Okay, this is second section, 3 through 6. We're given a polynomial. F of x equals x cubed minus 3x. We know what we're going to have to do. We're going to have to find the first and second derivatives, determine where they're positive and negative, and equal to 0 in order to answer these questions. So let's do it. Let's take the first derivative, 3x squared minus 3. Thing to do, factor out of 3, and factor x squared minus 1. If you can graph the first derivative, the graph is the easiest way to determine where that derivative is positive, negative, and 0.
Slide it over.
Thank you. Okay. So let's do a graph of the first derivative. What we have here is a second degree equation. It's a parabola. It's concave up. It has zeros at -1 and 1. This is what I recommend you do. Okay? Because just by looking at the graph now, you know where that first derivative is positive. That first derivative is positive when x is less than -1. It's positive when x is greater than 1. That first derivative is equal to 0 at -1 and 1, and it's negative between -1 and 1. Just by looking at the graph, you know everything you need to know about that first derivative. Well, we're going to have to do the second derivative too. Let's do that as well. Second derivative is 6x. And again, if you take a look at the graph, it's a linear function. It's a line. It looks like this. And that tells you where the second derivative is positive when x is greater than 0. Where the second derivative is equal to 0, add 0. And where the second derivative is negative when x is less than 0. Okay? It tells us everything we need to know about the second derivative. All right? Let's look at the graph of the function. Well, here's what we know. Since the first derivative is positive when x is less than -1, this function is going to be rising when x is less than -1. This function has a horizontal tangent at -1, where the first derivative is equal to 0. What I'm going to do is substitute in -1 into the function and find out where that horizontal tangent is. I'm going to substitute -1, where the first derivative is equal to 0, into the function itself. That's -1 cubed minus 3 times -1. That's -1 plus 3, that's 2. So at -1, 2, we have a horizontal tangent. Okay? Where else do we have a horizontal tangent line? We have another horizontal tangent line at 1. Let's substitute 1 into the function. You get 1 cubed minus 3 times 1. That's 1 minus 3, that's a -2. So at 1, -2, we also have a horizontal tangent line. Okay, first derivative tells us the graph is rising, less than -1, has a horizontal tangent. It's falling between -1 and 1. It's falling here. We also know this graph of the original function has a y-intercept of 0. When x is 0, y is 0. Goes right through the origin. Has a horizontal tangent. And then what? Starts rising again where the first derivative is positive. Okay. Now let's verify this with the second derivative. The second derivative is negative when x is less than 0. That means it's concave down, and sure enough, it's concave down there. It's equal to 0 at 0. This is a point of inflection at 0, 0. And the second derivative is positive when x is greater than 0, and it's concave up there. We can answer the questions. This is how I recommend you do it. 3, where the graph is rising, when x is less than -1 or x is greater than 1. 4, Horizontal tangents at x equals -1 or x equals 1. Just want to make sure that's how I ask. I only ask for the x coordinates of the horizontal tangents in the test, so this is all you have to do, is just like I have it here. 5. Where is the graph concave up? It's concave up when the second derivative is positive, when x is greater than 0. Concave up. Where is the point of inflection? At x equals 0. Okay. Any questions on that? Okay, do the next section, 7 through 12.